Einstein's theory of special relativity, and it was set to unify Newton's ideas with Maxwell's ideas. Newton had his law of gravitation since the early 1900s, but there were certain weird things that didn't quite work with that. So his special relativity also links space and time, and then he proposed general relativity about 10 years later, and that proposed that matter can cause space to curve, kind of like the picture in the background. That explained a lot of the universal exceptions to Newton's law of gravitation. So we're going to start with a little history, and this all came about because we discovered that the atom could be divided. John Dalton was the first one to have a lot of postulates and ideas about atoms, and he said that the atom could not be divided in 1803. That took almost 100 years for us to change our minds about that when J.J. Thomson discovered the electrons in his cathode ray experiment. Ernest Rutherford then came along a few years later and discovered that there was a nucleus within an atom. And then Chadwick came along 20 years later in 1932 and discovered the neutron. So this posed some questions. It showed that nucleus consisted of protons and neutrons all packed in together really closely. But the question was, they knew neutrons were neutral, so that's no big deal. But protons all had positive charges. So how are all these positives sitting together? Because we know from electromagnetism and electrostatics that two positives like to push apart and repel. So why didn't the atoms just split apart? So they ran over this several times, and the conclusion they came to was that strong nuclear force, there must be another force there, and that's the strong nuclear force. So how it works is it is able to keep that nucleus together. So it's actually stronger than the electromagnetism that's pushing those positive charges apart. It only works on a very small distance, like a nucleus, and it's derived from the neutron. So, even though nuclear force is much stronger, it's actually 137 times stronger than the electromagnetic force, and it's the strongest of all the fundamental forces, the range is much smaller. Okay, it can only work on that nuclear amount. These interactions between protons and neutrons were first explained by a Japanese scientist named Yukawa in 1934. So let's look at some ways we know that we have some of these forces. If we look at star formation, a gas cloud of hydrogen becomes so dense that heat and pressure and gravity cause it to fuse together to become helium. This actually is coming from our fourth fundamental force, which is weak nuclear force, and it allows the hydrogen to fuse together. So let's look at a weak nuclear force. Another example of a weak nuclear force is that neutrons can decay. Okay, so it's allowing them to change. It becomes a proton, and it can emit an electron. So that little part that's cut off there, the white, that's a neutron, and it's splitting apart on the bottom right corner there to become a proton and an electron. This process is called a beta decay. Okay, and the force that destroys that neutron is called a weak nuclear force. And that decay causes the atom to be a different element. So if you look at first, it's cesium in the big picture, 55, and then it becomes barium, which is 56. So where did this come about? In the 1930s, Enrico Fermi described this as a force that required contact, but now we know that weak force does not. It just has a really short range. It also is not as strong as our strong nuclear force or even electromagnetism. It's actually third out of four. So our four fundamental forces, we have strong nuclear as the strongest, but it has a very small range. Electromagnetic is the second strongest, and it has an infinite range, which means very, very large. Weak nuclear is the third strongest, and it has the smallest range of all. And gravitational is actually, gravity is our weakest force, but it has a huge range that it can affect. So, some other applications. We have nuclear fusion and fission, and they happen because of nuclear strong force and binding energy. So just to review from chemistry, a fusion, or to fuse together, is when you take two small nuclei and they stick together or fuse to form a new larger nucleus. So two separate come together as one nucleus, and that releases a lot of energy. Fission is the opposite. So you have one nucleus splitting apart to form two. So it's going backwards. And that was discovered in 1938, which led to the use of the atomic bomb. Some applications for nuclear ideas: radiation therapy, used if like there's a tumor, they can use radiation seeds or beam to attack that. Diagnostic imaging can be used, okay, like MRIs. And nuclear power is also another good application for nuclear phenomena. Some quantum applications, quantum meaning the parts inside the nucleus. Digital cameras are an application of that, and a lot of our modern electronics are based on that, and it's really the transistors, and we use those transistors in computers, games, lots and lots of things. Lasers is an application of this. Laser actually stands for light amplification by simulated emission of radiation. So light amplification means it's making it bigger, and it's simulated emission, so it's causing those light photons to be released. Radiation is light. These are set only to emit one color of light, and they simulate electrons absorbing and releasing energy at those specific frequencies. Okay, stars. Then we can also apply this to stars, and stars are mostly composed of hydrogen and helium. So why would this be the spectrum of the sun? We recognize sun is a star. So why would we have all of those if all they have is hydrogen and helium? Well, it's because hot, dense bodies, the stars and the sun, are very hot and dense. They emit a continuous spectrum regardless of what they're made of. However, those black lines are actually important. Stars' composition, so you can see what different gases are in stars, can be determined by the absorption spectrum instead. So instead of getting that emission spectrum from stars, you get the absorption and you're looking at the negative and looking at it in reverse. So the gases have absorbed the energy at their specific emission spectrum, and that's how you can go through and determine what gases are inside a star.